Okay, so the next talk is about what's happened since the last ice age. Ken took us kind of all the way through and a little bit through the last ice age, but that's where we're going to start. And so the deep past basically was when we had the last glacial maximum, and that was 20,000 years ago. And when we're thinking about the planet and we think it's gone back 4 to 5 billion years, 20,000 is like a blink of the eye. And today I'm going to say, back then the sea level was 400 feet lower than it is now. So since the last glaciers were here at maximum, the sea level has already risen 400 feet. And also we can see that the last ice age, of course, ended with a huge warming. And that's why the sea levels have risen 400 feet. Now, back then, the CO2 that we've been talking about was 180 parts per million. Today, it's 430 parts per million. So CO2 has more than doubled since this time. And Ken is right. The rate of change is what we're really talking about here. But back in that day, Florida was really a refuge for species. And it still is today in many ways. But Florida was a very special place. It still is. And back then, it was really a refuge. So Ken talked about the end of the dinosaurs when the asteroid hit down in the Yucatan. That was 66 million years ago. And he also talked about all of this time back to the beginning. And I'm just going to put this on here now to show you, it's been a long time, and Ken talked about all of it. And I am going to talk about where that star is, from that star to 200 years from now. So the very near past, and the question we're going to answer is, what can we do about it? Can we learn from the past so that we have the future we all want? So we talked about human population and how human population is really driving the show. But that little star, that red star right here, is the same red star I had on the last slide. So we're not talking about anything before then, but this is 10,000 years BC. And you can see the world's population back there, 4 million. 4 million people, 4 billion years of evolution, and 4 million people. And we reached about 1 billion people in 1800, a little less. And between 1800 and 2025, we've gone from 1 billion to 8 billion. And of course, as we modernized our society, we've put a lot of CO2 in the air to do it. And so this is the last 800,000 years of CO2, and I wanted to show you the trend. Ken showed you this too, but the yellow star is basically around the time when the human population reached in the millions, just a few million. And since then, you can see it. We actually had quite a cold time at the beginning of the human existence, and human beings didn't really, weren't able to really inhabit the earth like they do now until the climate started warming, coming out of the last ice age about 24,000 years ago. And so that little red star at the end there was where we're talking about in my talk today. So CO2 timeframes matters. And back, in the day, 15,000 years BC to 1850, the rate of CO2 increase was 5,000ths of a part per year. However, since 1850, the rate is 0.81 part per million per year. And in the last 5 years, it's 2.5 parts per million a year. That's 500 times faster than normal climate, changing from hotter to cooler, cooler to warmer. The increase has been 500 times. So when Ken says it's the rate, he set me up. We didn't talk about it, but he already knows this, and that's why we resonate as two little parts of the species. So back 100,000 years ago, when the Earth was just about as warm as it is now, Florida looked like the green area. And then 18,000 years ago, when we had all the ice, Florida extended all the way. It was a big state before it, of course, was a state. But you can think of it, all of the Florida shelf, going all the way to the edge of the Florida shelf, was all landmass. And now today, you can see what it looks like, and it shrunk about 100 miles already from sea level rise coming out of the last ice age. So things are changing. Again, let's look at it. That red star is 100,000 years ago when Florida was big. And here's where we are today. And you can see the rate of change of CO2 is massive. This is the same image, 800,000 years of history, where we never had CO2 anything close to where we have it now. So now I'm going to talk about just the last 12,000 years or so, because that's where we put the star, where we came out of the last ice age, and you can see it right there. And coming out of the last ice age, at that time, there were only around 5 million people. And you can see how fast the climate warms coming out of an ice age. That's natural. Coming out of an ice age is when we have the most rapid warming. But look what happened about 10,000 years ago or so. The climate became very stable. The temperature was very stable. We call this the stretch. And in the stretch, right there, that's where the human race really took off. When the climate was within 1 degree for 10,000 years, it never varied more than a single degree. And during that time, the population went from 5 million to 3 billion. 5 million to 3 billion. So we have a very sensitive species, our human species, even though we can adapt now with modern technology to keep cool. Just look at Florida. People couldn't live here before, but now we have 23 million people. Why? Because we have air conditioning. If we didn't, how many people would be here? It would be a lot less. So I want to go back to what we call the Younger Dryas. Again, look at the time, about 12,000 years ago, and this is Greenland only. And you'll see the red. The red is the temperature, and you can see over just 1,000 years or so, holy mackerel, the temperature just dropped. And that's not that long ago. What made that happen? And this is just on Greenland. And it's about 30 degrees that the temperature dropped in a short amount of time. And then just as fast, it went up more than 30 degrees. What the heck happened? This is what we call regional climate change. While the whole world was warming, suddenly Greenland warmed quickly, and then the temperature collapsed. What happened? Well, back in that day, there were two huge ice sheets over the North America, not counting Greenland, three counting Greenland. But you can see how far the ice penetrated down into the central part of the country. But during this time, and slightly after, the Earth was warming very fast coming out of the Ice Age. And this is what it looked like with Greenland. And you can see all that ice up there. But the pathways for melting ice were down through the Gulf of Mexico and then up into the Arctic and then out the St. Lawrence Seaway, what we know today is the St. Lawrence Seaway, into the Atlantic, sort of just south of Greenland. When the ice started to melt, a gigantic inland lake formed from the melting water, but there was ice all around it. And at a certain point, the ice dams broke due to the heating and released all that cold water into Hudson's Bay, down into the Gulf of Mexico, and up into the Arctic. And that little circle up there shows the area where there was a mass amount of very cold water that suddenly went into the ocean. And we know that we have this big conveyor belt called the AMOC, or the Atlantic Meridional Oscillation Current, that brings the warm water up from the equatorial areas up along the Florida coast, what we call the Gulf Stream, and then it goes up toward Canada and Europe. And the cold water comes down and circulates around, and this is the big conveyor belt. Well, this is what we think it looked like back then. But when all of that water came into the ocean, what happened is it stopped this current. Such a huge amount of cold water stopped the normal circulation, and the current just stopped. And so that's a big change. So while the rest of the world continued to warm, because we didn't have the Gulf Stream going up toward Europe, Europe dropped 10 degrees to 20 degrees Fahrenheit. And the population in Europe actually went down during this time, while the rest of the world was booming from a population point of view. And that's what we call local climate change forced by something breaking down in the system. So remember this now, because we're going to come back to it in just a bit. So when the megafauna, all of our big animals during the time, we had lots of them right here in Florida. Two things were happening. One is the human population was growing fast, and they needed to eat. The second thing that happened was rapid warming of the Earth. And as that happened, their habitat started to decrease, and they became a food source. So the reason the megafauna disappeared was not just because of the climate changing, it was because human beings were now inhabiting the Earth in the millions rather than the hundreds of thousands. And of course, this is actually, I think this is up, Pam is going to be talking to us in a little while, but I believe this is up in her neck of the woods right now. And this is one of the megafaunas that were roaming Florida in large numbers back in that day. So again, let's look at this. This is the last 10,000 years, and you can see how fast CO2 is increasing in the atmosphere. Greenland now has 10,000 feet of ice. Imagine that, 2 miles high of ice sitting in Greenland, and it's melting. In the last 5 years, 5 trillion tons of ice have melted, And that little circle I showed you, that's where it's all going. And so the AMOC in the last 20 or 30 years has slowed down something like 20 to 30%. Should that stop, we'll still get warmer. But if you want to have winter, you'll have to go to Europe because it will cool down very quickly. The European continent will cool down very quickly if the AMOC should stop. So the key thing about greenhouse gases is when you put them into the atmosphere, they have a lifetime. CO2 in the atmosphere is really active for 800 years or so, but the first half of it degrades after 20 or 30 years. So once it's in the atmosphere, we have a big response from CO2, and then half of it leaves, and the rest of it stays active. So it's a cumulative type thing. So that's true of the other greenhouse gases too. The carbon and the temperature move together, but there's a lag. So first the carbon goes in the air, and then the temperature responds. So we see this in the caves, and we can see the history of the Earth in these caves. And one of the things we see here is this tight coupling of CO2, but we also have, all of this research data now that we never had before in ice cores, in marine sediments, in the caves, and we can look at what's happened in the past, and we can see how fast things have changed. So with the tools that we have today, we don't have to guess about what the past was like. We can see what it was like. And so it's not just a story. It's not a parable of any kind. This is science at work looking back. And the reason why we can be optimistic about modeling our future is because we sort of get how it all happened. And this knowledge is power. So back in the day, the Holocene, which is what we're talking about today, we can see that, it was the end of the cold period, the megafauna diminished, and, it's the beginning of the age of man. So how much longer is it going to last? Well, I bring you back to this. This is the temperature since 11,000, 12,000 years ago, and you can see how it went up and down within the range of about a degree, and then what happened, basically, really since about 1950. These are the ice cores out in Colorado that are stored in a massive warehouse from all the glaciers around the world. We have them all in a huge, huge building, and we can tell exactly what the atmospheric content was at any one time by going back in the ice core, because we have spectrometers and other instruments that can tell you on the day, so to speak, how much CO2 there was, how much oxygen there was, what the constituents were. So we know how it's moving in time. And this is since 1950. And you see those little wiggles? That's summer and winter. And so an upward trend, and the rate of change is just amazing. And that's the issue, not so much the absolute value. Back in 1957, the Russians launched a little thing called Sputnik. We were all asleep at that point, but that seemed to be a wake-up call. When that thing started orbiting the Earth, everybody went, oh my God, we're really behind in what's going on. A result of that was the creation of the National Center for Atmospheric Research in Boulder, Colorado, where I happened to spend some of my career, and I was very fortunate to be a director of the university corporation that runs the National Center. This is I would say, it's just an amazing place. 1,000 scientists and engineers, the largest supercomputers pretty much in the world, The first global climate models were modeled here. And this is where the climate forecasts began. Back around 1985 was when we knew all the theory, but we could run these models backwards and forwards and create old climates and the forecasts for the new ones. And those models back then, if anything, have a little bit underpredicted the rate of warming that we have seen since then. So again, since our lives started, that's what it looks like. There's the stretch. And then boom. So if we put the whole thing together in one image, this is what it looks like. From 20,000 years ago, you can see the warming, and then we reached the green zone where the temperature did not change more than 1 degree. And that's when the human race really took off. And now you can see this is temperature that since 1950, we're up there right now, right at this part. We've broke 1.5 degrees centigrade, and that is where the beginnings of climate instability happen, where we could have things like the AMOC come to a halt in the future. And we definitely don't want that to happen. This is the world population since then, again. And I thought we'd put, my family on here. There is a time lag because I'm not allowed to tell true ages. But this is kind of what it was. So my grandfather, roughly 1879, and you can see the world population then was about 1.8 billion. When my sister was born, it was only 3. There she is. My cousins, they're right back there. My nephews were born in 2012, and here we are. So it's all happening right now in our lifetime. So this is the way it was, and this is the way it is. Let's look at that again. Before, now. Before, now. What a dramatic change we've seen. Since the last few years, since 1981, that red ring is the amount of normal sea ice in the Arctic. And what you're looking at today, the white, is what it looks like now. And you can see how the Arctic ice is shrinking over time. And what's happening is there's permafrost all around the Arctic, and it stores a lot of CO2 and especially methane. Methane is 50 times more powerful as a greenhouse gas than CO2. So when that happens and is released, it increases the rate of warming. And when the ocean gets dark, instead of the sunlight hitting the ice and being ejected back into space, it is absorbed by the oceans. And that's why the oceans are warming fast now. And when you warm the oceans, they expand. It's thermal expansion. So here's the temperature, looking at it another way, back to the beginning of the Industrial Revolution. And it's hard not to see that trend, right? It's uniform and it's not very bumpy. It's just continuous warming. This is how it looks on the stripes, where the dark blue are the coldest years, the pink and light blue are sort of in the middle, and the dark red are the warmest years. So when we look at Florida biodiversity, we have about 400 species in this state that are endemic, which means this is where they were created. This is where they are. This is our biodiversity. And many of these are now under threat. And there's really a couple of things going on. Since 1970, Ken talked about how many of the species have been decreased, but it's 73%. And we're seeing all of these impacts, but we're also seeing noxious species coming into the states. And we know about the Burmese pythons, for example, and they're proliferating in the Everglades. And when they do, they go after our native species because there are no predators, these invasive species. That's why they're invasive. And on top, you see Florida with all the green areas. The dark green are areas that we've conserved. The light green areas, and we're going to talk a lot more about this afternoon, are opportunities for us to conserve this land. And the reason it's so important is because this protects the habitat for the biodiversity we do have, but it's also a huge carbon sink and water purification system for all of us who live here. So it's very important that we take the chance that we have and make it happen. It's not that we don't want development, but we want climate resilient and biodiversity resilient development now, because it's very important to us as individuals. And these are some of our species that are at risk. There are many more, but these are the ones that you probably relate to. And so, it's amazing what animals do. People really feel a relationship to it. They see them and they say, oh, we want those around, I mean, I like the manatees a lot. They used to be in my backyard in Longboat Key. My little granddaughter, who was in a yellow tube and 1 year old, we were out in the Gulf, and one came right up right in front of her and looked right at her, scared the ever-loving daylights out of me and her father who were there. And those manatees came back every single day to see my little kid. So there is that connection we have with our past. This is what Florida looked like in 2010 from the point of view of precipitation in April. The dark areas are dry. This is what we think it'll look like in 2080. Quite a big change in a wetter Florida in April. Mm-hmm. So again, let's look back at when the last time we had a warm period like the one we're in that was anything analogous. The white areas are where the shorelines used to be. So here's the key thing. We're going to have, the oceans are going to rise because of the carbon in the air now. But the rate at which they rise is our choice. We can have rapid sea level rise, or we can have slow sea level rise. That's the choice we have now. You can see what it looked like the last time when all the carbon was engaged. This is what it looked like. These are the species we have in Florida. If we have 1 meter of sea level rise from where we are now, which is quite possible in the next 100 years, about 50% to 80% of all of our species will be impacted, and our endemic species in all these different areas will be impacted. So the blue is all of our species will lose 50% at 1 meter. And you can see how this works in the various subtypes. So amphibians will only lose roughly 20%, but in plants, we could lose 60%. And of our endemic species, you can see a lower rate there. But it's very significant. So here are the key takeaways. And I do want to say that, birds are part of our species, and the mockingbird is the state bird of Florida, but the lark bunting is the state bird of Colorado. and he's a climate expert. And we have a lot of painted buntings here, and some of them are in the audience. So I told you a little bit about invasive species, but this is how it works. First, the introduction of the invasive species, and because it doesn't have predators, eventually it comes around and it's settled in and becomes, if you will, native to where it is, and then it really speeds through and it helps degrade our endemic species. So this is why we don't want a lot of invasive species. In Florida, for example, you may be surprised. It's a very unique place in the world. 1,300 miles of coastline, and it's a peninsula. And it's the most biodiverse state in the United States. The most biodiverse state. So we live in an absolute gem from a point of view of biodiversity. As we go from 1.5 to 2 degrees centigrade, we all love the coral, we're learning about it. At 2 degrees, we will have lost 90% of it. In 2075, this is what we're expecting. And by the way, those are aphids on the leaves there, part of our biodiversity. So we're looking into the future a little bit here, and there are different futures that lie ahead depending on what we do. If we can slow down the rate of warming, we'll see these kinds of issues in the various areas. This is the Mediterranean, and this is Florida. At 1.5, you can see what it is. And at 3, you can see what it is. For every half degree or so centigrade, there's major changes to what we're going to be seeing. This is worldwide, but this is drought. The average drought right now is about 2 months, and at 3 degrees, it'll be 10. That's huge. That's 5 times more drought with just doubling the temperature rise from 1.5 to 3. Our mammals, you can see the difference here as we move up. I have 4.5 degrees here because it's still possible we could get to 4.5, less likely than it used to be, which is good. We're making some progress. And of course, in the Arctic, imagine at 3 degrees, I'm just going to say that our government was never interested in Greenland. But suddenly it's very interested in Greenland because they see what's happening, they know what's happening, and it's become a strategic issue if it doesn't have ice on it. And so that's what the conversation's really about, even though you'll never hear it that way except from me. And so James Hansen, who is an idol, he's one of the scientists of my time, and he was the chief scientist at NASA. And he probably is the smartest living scientist on this whole picture. And he's been putting out these warnings about what's going on and how fast it's going on. But you may remember, it wasn't very long ago when we stopped fossil fuels of a certain kind on big boats taking people and cargo across the oceans. And when we did do that, it cleaned up the atmosphere. All of that pollution in the boundary layer was masking the climate warming because it was absorbing the heat. But now that that's gone, we've seen kind of a jump in the rate of climate warming. And so in a way, it's kind of a perverse thing to think about that we cleaned up the atmosphere and now we're seeing the warming. But it's a really interesting thing. And of course, what he says is that even by the mid this century, the risk of the AMOC slowing down to a point where we see abrupt climate change in Europe, for example, is rising. So we don't want to get to those tipping points. In 2125, just 100 years ago, this is what we feel is going to happen if we stay on the same course we are on now. This is the projected sea level rise for the next 200 years, the red line, and on the left-hand side, this is meters. So 39 inches in a meter. So you can imagine 2 meters of sea level rise would be pretty catastrophic for a state like ours where half of it is below 10 feet. And of course, that would have a big impact on our species, right? Because most of our species are along the coastal areas. And this is the projected biodiversity loss by 2025. And this includes all of the things that we are now doing to slow the rate of change down. So the curve is flattening, but not enough. Is this inevitable? Florida in 2025 again? So what choices are ahead? We can have collapse or we can have stabilization. That's the choice. And how can we do that? It really depends on the amount of mitigation we do in the long term and the amount of adaptation we do in the short term. We need to do both at the same time. The past really has taught us that this is a real issue, and we should learn from the past. Is there anything we can really do? Well, here's the good news. Here's the optimistic part of it. There's a lot we can do. We can adjust to the impacts we have now and are going to have because we pretty much know what they're going to be. And so adaptation will get us through the rough patch of the climate that we're seeing, and we've sure seen it here in our local area and all of Florida in the past few years, but it's not unique to here. It's happening all over the world. And mitigation really is about lowering the carbon in the atmosphere so that we slow the rate of change of warming. It's the rate of change that's important, not the absolute amount. And just hot off the press, there's new peer-reviewed research that has just been released just in the last month of what we can do and what it will look like if we do the right things. Right now, we still have 12 inches of sea level rise that we can stop from happening by 2300. Mm-hmm. That's a lot. And if we just let the policies we have right now continue to 2050, there will be 12 inches of additional sea level rise by doing what we're doing. By 2090, if we don't change, that amount goes to 31 more inches of sea level rise. But if we do the right things, if we do convert our economy to be, or not just ours, the world economy, to being less fossil carbon dependent, we still have about 23 inches of sea level rise that we can prevent if we adapt and mitigate. That would be a game changer for Florida. So the choice that we have right now is to innovate, and we have the innovation. It's amazing how fast we're innovating. You're going to hear about some of those innovations in the rest of this day. And this is the hope. With the scientists we have here today and what they're doing, it's an amazing opportunity for us to innovate and get there. No one knew what AI was in this audience, really, 3 years ago. And today, how many of you are using it? Look at that. Okay, so that was 3 years ago. This is an eon compared to that, if we decide. So this is our beautiful coastline that we're looking at right now. If we adapt and mitigate, we will not have this. But this is what it will look like 100 years from now if we don't. That's why we want to make Sarasota a living laboratory for climate adaptation. And our next conference next year is going to be all about that. And we hope all of you will be here for that. Thank you. Be optimistic, be informed, and be engaged. Good. All right, let's have some questions.
I have one over here. So I got a question. Do you think AI... Oh, pardon me. Thank you.
Oh, there you are.
Hey.
Thank you.
Professor Sean Patton here. Do you think AI and the quality of work that it produces is worth the huge amount of energy we use fossil fuels to produce, the massive amounts of land we strip mine to make these AI data centers, the art that we steal from artists, professor at Ringling College of Art and Design? Do you think the AI that we're using is worth it? Do you think it improves the quality of our lives or presentations?
Well, it's a great question, and I wish I had the answer for you.
Manslaughter, actually.
So, one thing we know for sure is there's going to be progress and there's going to be technology innovation, and that our world is driven by economic success. And that economic success has led partially to the population we have, but it's also, we've never had so many people living so well on the planet as we do today. So there are pluses and minuses. The thing is, how do we manage all of this? Because no one is going to go back and live in a cave, and I'm certainly not going there either. But technology itself is agnostic. People who use the technology are the problem. How the technology gets used is the problem. And that really is a human condition issue. It's not a technology issue. You look at nuclear power, well, some of these new data centers are going to be powered by nuclear power, okay? I mean, some countries are powered by nuclear power, and we decided to turn back on that because we were worried about the 1/1,000,000th of 1% risk that it had. Now we're going back to it because we realize so many of the other risks are way, way, way more risky. So the thing is that AI is going to be amazing, but how it's going to turn out is going to depend on how it's developed and how human beings deal with it. That's about the best answer I think I can give you.
So AI is like another right now. Nuclear energy can be.
Thank you. Nuclear energy has an obvious purpose. It powers cities. I have not seen any true use come out of AI. It's replacing a lot of mid-level jobs by taking the work of others. And the quality of the work is not good. Again, how many arms did that caveman have?
Well, don't forget, it's only been out in the public for 3 years in our first...
But we've destroyed lakes, forests, mountains.
I understand. I understand what you're saying. But once we had horses and there were 1 million people who were in the Pony Express, And 10 years later, we were all driving in cars, right? And the cars weren't that great then, but they are. So, I mean, I'm not saying that all of this hasn't happened. I am saying it has happened, but I'm saying that we have options for dealing with it that we have to take, because we're not going to turn back these issues. People aren't going to walk away from AI. The only thing we can hope to do, and by the way, in weather forecasting and in climate forecasting now, AI-driven models are almost as good in just a short amount of time as 100 years worth of geodynamic models. So AI is already helping in the age of weather and climate forecasting, and it's going to get a lot better. And by the way, we're going to talk about that during next year's conference. It's going to be focused on AI and its uses for science.
Is it work?
I don't know.
Yeah.
I can't tell you that now.
We'll find out. I hear they're already working on the first net zero AI. Just kidding. Yeah, I mean, I mean, it's going to be interesting to watch it evolve. There's going to be a lot of benefits for sure. By the way, your sister right here just really appreciated putting her birthday on there, because she's going to get a lot of cards and presents next year for her birthday. Okay, right back here.
I have another question back here.
So watching these presentations just makes me want to cry, because the future looks so bleak. We have innovations. There's a lot of people dedicated, doing studies and so forth. But there's no political will. You know, the vast majority of the people don't give a damn, frankly. They can't look 200 years in the future.
Well,
They're looking at putting food on the table and so forth.
well, the human condition is what it's always been. As they say, in the human condition, there's nothing new under the sun.
Yeah.
On the other hand, in humanity, in all the times that we have been here and when great changes have been made, history shows it's only 5% or 10% of the people that affect that change. So, inertia is a big, big thing that works against us. It does protect us in some ways because we don't make changes too fast. But it's also something that we can overcome, because it doesn't take 80% of the people to make the change. Most people adapt to what's happening when they see the value of it. If you ask them today what kind of a car would they like to drive in 2050, they're going to tell you the car they're driving now. But when they see the new ones, they're going to want them. So that's how it works. I wouldn't be pessimistic about it. I would feel optimistic about it, because it doesn't take everyone to decide. It takes the leaders to decide. And by the way, our whole goal at the CAC is to inform the leaders in business, in government, in philanthropy, and in the public about where we are, so that they can be the vectors of change. I can't do it on my own. The only reason we're doing this is because of you. I already know. But I'm trying to get you out of your inertia. But we have to learn what the issues are first, and then you guys have to get busy. There's nobody out there who's going to do it for you. And when you look at governments follow the people. They do not lead the people. That's how it works. When the people are upset and want something to change, it always does. But if you're satisfied with the way it is, then we can tell you what's going to happen, pretty much, in a high percentage. We can't tell you exactly, but we can tell you the trends. And the trends are always your friend until they end.
Huh?
So we have to be engaged in our own future, and I am sure we will. And all the scientists here, look at what they're doing. And look at the innovations we had. And when you hear the rest of it this afternoon, I think you will be amazed at the rate of progress that we're having.